All right. So I'm going to talk a bit about, on behalf of some of my colleagues, some work that we've been doing with Llama CPP to add a new backend that takes advantage of some of the work that we have within the foundation. So if you haven't heard of Llama CPP, there's an article that the original author of the project has written, just explaining, how they kind of got to where they were. So he had this project called Whisper.cpp, and he saw an opportunity to start this project Llama CPP. But you can see the red chart of GitHub stars. This is a little bit old, but it's the one that he uses. You can see how popular it got really, really quickly. And part of the reason for that is PyTorch is obviously good for, if you have a powerful environment, if you want to do lots of training with large models. But I think what he identified is that there wasn't really something that existed that didn't require lots of dependencies. You might want to use it offline, or you might not want to use it on you might not have access to the sorts of machines that you need for some of the models with PyTorch. So it was originally intended as a lightweight C++ framework for doing AI inference, with support initially for the Llama model. But now it supports many, many different models that you can use. Has bindings with Python, so if you prefer to use Python, you can do that. The community is adding a lot of things around it, so it's really become a very, very very popular project. The other interesting thing, I suppose, because it's being driven by an individual from the community more than a particular organization, there's a lot more openness around adding different backends, and this means that it supports a really broad range of processors and different ways to use it. So you're probably all familiar with the sorts of things that you can do with large language models. This is the kind of questions that you can ask. Text queries are fed in by command line or via API. The one thing I suppose about Llama CPP, which is different from PyTorch as well, is that it gives you a lot more control over the execution, the performance, the optimizations that you use. And that's, I think, part of the reason it's made it popular, I guess, in particular with people in lower powered environments or embedded. So obviously there's another project called Llama, but again, it doesn't give you the level of control that Llama CPP does. So another key thing about this project, which makes it useful for a lot of people, is that you can run models on a CPU in a kind of reasonable time as well, which means that you can experiment on any computer really, and it supports the majority of that. So I'd say that one of the differences between Llama CPP and someone like PyTorch is that it's been specifically built with limited resources in mind, and it allows you to fit quite large models on CPUs and like smaller GPUs, so GPU that you might have in your laptop. And the goals for this project was really to make it run models on a really wide range of devices, in particular desktop PCs, but laptops, embedded machines, and things like that. And one of the, I suppose, unique things as well is that you can use it offline, so you don't need an internet connection if you want to run the inference locally, which is pretty interesting for certain use cases. I've put up here the different backends. The one that I'm going to be talking about today it's called the SYCL backend, so it combines SYCL code with some of the UXL libraries, so 1DNM. But you can see, this Vulkan backend is OpenCL backend that supports different GPUs. All right, so I suppose I wanted to talk a bit about how it's possible to run larger models on lower powered machines. Because when you look at it at first, the sort of memory requirements that you would have seems to make that seem impossible. So the project uses this technique called quantization, and this is what makes it possible to run these larger models on smaller devices. So typically, if you run a model like Llama 2, it'll have 7 billion parameters. It will require you to have a multi-GPU server, which most people don't. But what you can do is, or what Llama CPP does, is it reduces the precision of the types that are stored in the data from 32-bit to 16-bit, and that allows you to fit it on a discrete GPU, for example. But then, if you use some of the custom quantization techniques that Llama CPP provides, you can reduce the size further so that you can fit it on like a normal laptop or desktop machine. And one of the clever things about the way that the project uses this quantization technique is that it doesn't suffer from any significant degradation of the model and the results that you're likely to get. So I'm just going to talk about this at a very high level, because I'm not an expert in this area, but you've obviously got LLMs have two main parts. I'm going to talk about one of these today. You've got the prompt processing, so you type something in. These get turned into tokens, and this is what's processed by the framework in order to start predicting what the next word should be and give you the output. So this is, again, to set the context of how this fits in with the foundation libraries. So this gives you a view of how the operations that are needed to process the text are laid out. You give it an input set of words, then based off all these different operations, it tries to look up all the input, decide which ones are important, and then give us the output prediction after that. So I'm going to focus on the attention part, as this is the bit that's relevant to the work that we've been doing with 1DNN. So during this stage, you can see there's an obvious area for, I suppose, optimization, and could bring significant benefits. And you can see that it basically uses lots of matrix multiplications, which is a common technique that's used in neural networks. So you've got basically sort of a multiplied number of these happening, and so it ends up being lots and lots of these. So this was an area that we focused on within the Llama CPP project, and was an area that we tried to standardize on and optimize. And that's where the 1DNN library provides this optimized matrix multiplication operation that you can call, and that was what was used within Llama CPP. So you can see the 1DNN project provides these optimized routines for matrix multiplication. There's a variety of different supported types, ways to process different matrices, and so it allows you to do that through a single API. And you can look at the specification, the documentation that describes how that's done. So one thing I suppose that we're looking into the future with this is that by using 1DNN, at the moment, this has been tested on Intel processors and NVIDIA processors using 1DNN, but because it's multi-target, it's got the potential to cover more than that. So if you were building a project, you can call a single API, and then you just need to change the flags to tell it which processor to run on. Then obviously that's a big advantage for you and your project. So yeah, we'd be interested to see whether anyone within the community would be prepared to try that out and see how well that works. So that was kind of a short introduction to bits of Llama CPP and the work that some of my colleagues have been doing. You can take a look at the project, find out about the SYCL backend, and how it works. I've seen blogs and articles online that really show how easy it is to set up Llama CPP. I think you could do it really quickly and try it out. And you can build it with the SYCL and 1DNN backend. And also, the latest release has some good optimizations in there, which should be definitely worth checking out. You can see the increases in performance that have been achieved on different Intel processors in particular there. Okay, is there any questions from anyone? Okay, so I'll go straight into the next section before we have a bit of a break, and talk about how to get started with the UXL Foundation projects. And I'll start a bit by talking about a number of existing projects that are using the Foundation libraries. The GrowMax project, so this is, I think, one of the, or maybe the biggest or most popular, I don't know how that's exactly defined, science projects in the world. So it's using the OneMath library to target different architectures. So it's quite common in science applications to need to use, maths, and so using a single API makes it easier for them to maintain the code base there. NWChemX is another popular science application. This one's developed by some of the national labs in the US, and again, it's achieving cross-platform performance with OneMath. Ginkgo's a linear algebra library, similar sort of situation. You kind of get the pattern that there are lots of research that's going on in the US national labs that requires maths to be used, and so this makes it easier to develop and easier to maintain the code base that they have. Just talked about Llama CPP. Megan talks about PyTorch, but these are two projects that are using 1DNN extensively. The TensorFlow project is also using 1DNN for these optimized cross-platform routines that are available. And the last thing I suppose I wanted to talk about is just to help understand the benefits of being vendor neutral. So I've been working with folks from the US National Labs for quite a few years now, and when they were setting up their latest, I suppose, set of supercomputers, there's a bunch of different labs, as you're probably aware, Argonne, Lawrence Berkeley, Oak Ridge, and the like. And there was a goal to make sure that code could be portable from one machine to another. So we spend quite a lot of time working with them to make sure that the One API and SYCL software tools works across these machines. And that means that applications like NWChemX, the ones that I talked about, you can run them on any of these machines without without really any code changes that need to happen. So if you think about that in your own kind of environment, that if you buy some computers one day and they've got one vendor's GPU or CPU in them, and then 2 years later you buy another one, you don't want to have to go through developing the same software and all the porting that would go with that. So they've achieved that level of performance portability across their different machines and different labs. So I'll talk individually about the different projects that we have available within the foundation, what you might use them for, etc. And I'll talk also a bit about how you can get involved and how we're trying to engage with the broader developer community to get their contributions to this as well. So we've talked a bit about 1TBB. I'll go into a little bit more detail. So this is a project that's focused on CPUs, and it allows you to, as I say, fairly easily bring parallelism to your application without really too much effort. You don't need to know about CPU threading. I think anyone, including myself, that's tried to use threading using C++ gets pretty confused pretty quickly. And this provides a nice framework for doing that. It's commonly used, so it's used by lots of different projects on GitHub. It's also used by the, I guess, other libraries that are part of the UXL Foundation as a way to basically make them run faster on CPUs as well. For example, the G++ GCC compiler uses TBB for parallel STL. You can use it with ARM and x86 architectures, and the performance is scalable, as in, you see the chart going up in a diagonal direction as you offload work. So there's two types of parallelism that this library supports. The one that's most commonly used with GPUs is called data parallelism, and this is basically a way for you to split a common task across different CPU threads. And this, so for example, if you were adding two arrays together or vectors, then you could split the work up so that one CPU thread does half of it and the other does half of it, or however you decided to optimize that. The other type of parallelism, which I suppose is relevant in the context of heterogeneous computing, is when you want to give different jobs to different threads, like you might do with processors as well. But it means that, I think in this example, it's talking about an automotive situation, but you could give the display job to one thread, you could give the driver assistance to another thread, and so on. So, so if you want an easy way to try out parallelism on your computer with a CPU, then this is a good way to do it. So 1DPL, these are ISO C++ parallel routines. So within the foundation, we try to work hand in hand with other standards. And this project, this is what this does. So it uses familiar standards and projects, including parallel STL. There's also Boost, which is another commonly used way to do this as well, which is defined. And the way that this is implemented is that the kernels, as you'd call them, are all implemented using a programming model called SYCL. And this means that you can build them for any of the targets that the compiler supports for that. At the moment, you can use it with Intel CPUs and GPUs, and there is an experimental NVIDIA target, but as I say, because they're SYCL kernels, you can try them with any targets that are supported. Yeah, so this shows you the variety of the implemented parts for 1DPL as well. From C++ 17, there's the execution policies, and there's a whole bunch of things. C++ 20 has range-based algorithms. These are all things that you can use there, and more get added as they're defined. So some of you might be familiar with Intel's had a product called MKL for, I think it's like, I want to say 40 years, but it had some sort of anniversary recently. So it's been around for a long, long time. So this is kind of what this project was born out of. Recently, we changed the name to OneMath because it seemed more appropriate as a generic math library for us to use. But it aims to provide a common set of APIs that that applications are going to need to do maths for things like linear algebra, random number generation, DFT, and stuff like that. And I talked a bit about the projects that are using that library as well. This supports quite a wide range of targets. We recently added a backend for our ARM CPUs using the ARM performance library and the OpenRNG project. So yeah, as you know, as time's going on, we're adding to the number of targets that you can provide. This is just a brief code snippet just to show how the runtime dispatching works when you're using OneMath. There's a bunch of stuff for data in memory setup that I've not included, but it shows you how simple it is to set things up and then call this gem API on the data that you have. So we've talked quite a lot about 1DNN, so I maybe won't dwell on this too much, but as said before, the operations that it supports are really commonly used in lots of different AI applications and frameworks, and it supports a wide range of targets for different vendors. We're also seeing quite a lot of interest recently in adding for RISC-V within 1DNN as well, so I'm hoping to see some contributions for that soon, as more RISC-V, not only CPUs, but more GPU-like architectures come out and are actually available for people to get their hands on. This is just an example of how 1DNN is structured from a coding perspective. You have an engine that controls all the work. You set up memory objects, and the execution of the primitive is done through the stream. But it tries to simplify the way that you call these primitives. So 1DAL is used to accelerate big data analysis with some optimized building blocks for the stages of this analysis. And it works alongside scikit-learn, as you can see in this graphic here. And it helps you to speed up your scikit-learn applications quite significantly on GPUs and CPUs as well. And so if you're doing that kind of work, then worth investigating. 1CCL, I think I talked about this. This is more relevant if you're working in an environment where you have quite a big system, something that has multiple nodes. But this basically helps you to manage the transfer of data and work across those nodes, doing that efficiently. If you're running something like PyTorch, then it allows you to distribute the work across lots of different nodes and processes that you have on those nodes. It's built on top of MPI, which if you do have a big system, then you'll be familiar with that. One thing we haven't really talked about yet, and there'll be a talk later on about this, is we have this project that's called the One API Construction Kit. So the company that I work for, Codeplay, developed this over the last probably 10 years or something. It was made open source a few years ago. And this is really a framework for enabling new hardware to work with both SYCL, but also the libraries that we've been talking about as well. It specifically allows you to basically bring up an implementation of OpenCL with your hardware, and provides that interface so that you can complete the software stack. But we'll talk about that in a bit more detail later, about how that works and also how easy it is to use as well. So you can use the libraries today. There's a couple of ways to do this. One of them is to download the binaries that Intel packages on their website. As we've already spoken about, that does mean that you're generally restricted to running on Intel hardware. But if you build from the open source projects, then you can run on all the targets that the projects are able to support. And we are working on ways to make those open source builds and binaries a bit more easily available, so that we have, the community has a way to get those as well. All of our documentation is open source, as you'd expect. You can find it through the individual projects. I guess encourage people to contribute to that. For things that you see that are missing or need correcting, you can go to GitHub and you can make a pull request and help us to make the documentation better. It's built using Sphinx and Markdown, so it should be familiar to anyone who's done documentation stuff before. So I touched on this a bit earlier. We have 4 special interest groups that meet through the year. These broadly align to the projects. So we have the math one that obviously aligns with the math library, but also talks about future topics and use cases and things like that. The AI one aligns to 1DNN probably most strongly, but some of the other projects as well. But anyone can join these meetings. The details are available on our GitHub repo, and you can sign up for them by joining the group mailing lists. Yeah, and the notes and the recordings are also available, so you can see what's come up, and we're starting to try and publish those on the YouTube channel to make them easily consumable too. We do have a working group. In order to join the meetings, you do need to be a member, just because of the IP framework that the foundation has. But this group meets as predominantly maintainers from the projects, but also other interested parties, and this coordinates a lot of the activities that we're doing. We've been focused quite heavily in the last year on continuous integration, security, and things like that. But any member can come and make a proposal. Decisions are made democratically, as it says, and everything's done in the open. So, just to talk about a few ways to get involved. The first way, as we spoke about, is to try things out, download the binaries or build from the open source. We obviously welcome people to submit issues and bug reports or tell us what's missing, join in the meetings. And also, one thing that's crucial as well is if you do have an interest in some of these projects, decision making for them is open source as well. So we have an RFC process for all the projects that anyone can participate on in GitHub. We'd encourage you to do that to help us make sure that the APIs we define are good, any architectural changes that we make and new features are done in a way that you want. The second stage that you could go to is you can contribute to the projects. So you can help to improve the experience of these for everyone. So that can go from documentation, you could fix a bug or help us to implement new features, add new supported hardware and test on hardware as well. That's really important, and something that Chris will talk a bit about is performance benchmarking and things like that later on. And you can make proposals as well. So we'd welcome all of these things and ways for you to get involved. And the third way is kind of beyond those is contributing resources. So as we mature as a foundation, the amount of CI infrastructure, for example, that we need grows, and we need help from the community to make sure the projects have enough of that in place. So if you have machines that you can help us with doing that, then we would be really keen to hear from you. We'd also be really keen for people to test on different platforms as well. Obviously, there's only a limit to what single organizations can do. So if you've got access to RISC-V or whatever it is that you're most interested in, then we'd welcome you to help us with that. You can run the benchmarks. So running benchmarks on different hardware helps us to build a picture of how things are performing on different targets and where we need to improve. So that's something that, again, we're trying to work on improving. And then the last thing is really the open source releases. So something that we're working on within the working group is how we can make open source releases available to the community. And yeah, that's quite an important thing, as was brought up earlier as well. If there's anyone here from sort of academia or research groups, then we've recently set up this academic alliance. So it's for a lot of nonprofits, it can be quite hard to sign up to the member agreement that we have because of the IP frameworks that we use to protect our community. So we've set up this alliance, basically allows you to have access to speak at our events, represent us. We'll promote your projects that you're working on and do co-marketing and things like that. So you can find out more about that at the QR code. And the last thing, so we have a Get Started page on the GitHub repo that you can find here too.